Alright, so we're going to do an example. It's a pretty simple equation, really. Uh, with current I is the symbol for current. It's in units called amperes. Q is, of course, lowercase q is the symbol for charge, and that's of course in coulombs. And T is time. Excuse me, time in seconds. So here's our example. So current is I, and this is the actually the way it looks. It's the change in current divided by the change in time. And for all intents and purposes, well, not. Let me say, a lot of times, it'll just be the final charge divided by the final time, and both of them will start at zero. So this becomes just simply Q over T. All right. So let's go over the units again. I is in units called amps, and the symbol there, you can either write amps or you can write capital A. Q is in coulombs, so that's a capital C, and the time is in seconds. All right, so very quick example would be, for example, let's say Q was 8 amperes, and the time is 2 seconds. So that's pretty simple as far as examples go, but it really doesn't get much more complicated than this. And so it's 8 coulombs divided by 2 seconds. And as far as units go, a coulomb per second is also known as an amp. So this would be 4 amps. Alright, and so there's our first example. Well, that's it for this. Let's go back to our PowerPoint, and this is really one of the central equations. I mean, that last one is just defining current. So this is a big one. This is called Ohm's law, and so it relates, as it says it right down here. Ohm's law, it says that the voltage is equal to the current times the resistance, this quantity known as the resistance. And resistance gets this symbol, capital Omega. Now it turns out, as life goes, this is actually labeled. It really should not be called a law, not in any sense the way we think of a law like the universal law of gravity or the law of the conservation of momentum. Those are quantities which are always, those laws, I should say, are things that are always followed universally. And Ohm himself, back in the 19th century, when he discovered this, he found that there were certain substances where this equation, which is now bears his name, was not followed. It basically, that there were non-linear relationships between the voltage and the current, and so like I said, even Ohm knew that this was not truly a law of nature, but it's got this name now, and it's going to stick. Let's do an example. Here's our first example with Ohm's law. So let's repeat it. The voltage over a device is the current times the resistance of this device. And so let me draw a little picture here to give you a sense. So this is this long line and short line repeated represents a battery or a voltage source. This is a line, or a wire, I should say, that comes from that voltage source. And then this symbol right here, this squiggly line, represents what's called a resistor. Okay, so this is the resistor, this is the voltage, and basically what happens is current comes out of the battery on this side. By the way, this is considered, the longer end is the positive side, the shorter end is the negative side. The current goes through the resistor and continues to go all the way to the negative side of the battery. And this works as well with a generator. Let me draw that real quick so you can see. I mean, it's exactly the same. So a generator looks like this. You just put a little sine wave, and it's just a circle. And so here's the wire, and then here's our electronic device to make it more general. But this is the resistor. Whoops, that's supposed to be an R. This is going to be our voltage source, and of course this generator here gives us what's called AC. But it turns out that and of course what's happening with the current, this is really showing you the difference, is in one instant the current is going in this direction, but for alternating current, a moment later the current will go back the other way. And so it's basically like a battery that's flipping back and forth. Alright, so that's really the difference between AC and this situation, of course, is DC. So that just kind of emphasizing this idea. Let's go over the units. This is pretty simple. This is in volts. So it's the symbol V. The current, of course, we just had, that's in amps. So you could write out the word amps, you could write out the word volts. But the resistance is in units which have the symbol capital Omega, and that's known as ohms. Okay, so let's do a quick example of this. Alright, so let's say that we had a resistance of let's say 15 ohms. And ohms can vary. You can have less than an ohm. You can have very specialized circuits. And in some circuits, you could have many mega ohms, millions of ohms. Okay, so that's 15. And let's say our voltage is, a typical household voltage is about 120 volts. Okay, so a 15 ohm, let's say this is you don't have to define what it is, but there's just some generic electronic device over here of value 15 ohms. It could be a toaster, for example. That's a typical device that would be around 15 ohms. And as I said, typical household voltage is 120 volts. And so what's the current? How much current is going through that toaster? And so we use Ohm's law, V equals IR, so I is equal to V over R. Alright, so just from algebra, so it's going to be 120 volts over, I forgot, what was my resistance? Oh yeah, 15 ohms. And the units, the volts divided by ohms, give us amperes. Alright, so let me get my calculator. So this turns out to be, of course, 8 amps, which is actually a large amount of current. That's a very large amount of current. And so, the idea here is, you're always going to know two of these values, not the same two, but V equals I times R. So you're gonna, two of them. You can always calculate the third. All right, let's, I guess, just do another example. This is a completely different problem here. So let's say. All right, so now let's do. Suppose we had a current of 2.7 milliamps, and we had a voltage, so that's milliamps, and we also knew that the voltage was, let's say, the voltage was, oh, I don't know, how about 80 volts, okay, in some simple circuit. Then we could certainly calculate the resistance, right? I mean, so the resistance R is the current. I'm sorry, it's the voltage divided by the current, right? The voltage divided by the current, I. And see, we know V, we know I. Now notice I is not in the right units; it's in milliamps. So we have to put that in amps. So here we got 80 volts. And we're just going to use our metric prefixes here. So 2.7, and can you guess what the 2.7 milli is times 10 to the minus third? Times 10 to the minus third. Okay, and of course that's amps. And volts divided by amps gives us ohms. All right, so let's see, let's try this on our calculator. So when I plug it into my calculator, I get 29,629.6 ohms. And that is, that's that last example. And so that would be the resistance. It's 29,000. Just to let you know, sometimes if I were to move the decimal point, I mean, this is perfectly fine. That's the right answer. But often in electronics, they will give us an answer in kilo ohms. So sometimes you'll see this. So this, for example, would be 29.6 kilo ohms. Okay, so that both of these mean the same thing. So in the bottom example, I've just moved this decimal place 3 places to the left, and so that's how I get my 29.6 kilo ohms.